Today we're diving into a fundamental mystery that, no joke, powers our entire modern world. And it all starts with a question about the simple things you see every single day.
I mean, think about any cable you've ever plugged in. We all just kind of know that the metal part on the inside carries the juice, and the plastic or rubber part on the outside keeps us from getting a shock. But why? What's actually fundamentally different about those two materials?
And here's where it gets really mind-bending. There's this third category of materials, the stuff that makes up the brains of our phones and computers, that can switch, that can act like a conductor and an insulator. How on earth is that possible? All right, let's get into it.
To solve this thing, we need to zoom in, and I mean way, way in. We're talking down to the level of individual atoms.
So what you're seeing here is the foundation for everything we're about to talk about. See, in most solids, atoms aren't just a random jumbled mess. No, they're locked into this super organized repeating structure. We call it a crystal lattice. Think of it like a perfectly built atomic scaffold. This is the stage where all the action is going to happen. Okay, so what is electricity, really? When you get right down to it, it's just the movement of charged particles. And for pretty much everything we use, that particle is the tiny, negatively charged electron. So electric current? It's just electrons on the move. Simple as that. And here is the absolute key to the whole thing. An electron that's stuck, one that's tightly bound to its home atom, well, it can't go anywhere. To get an electric current, you need electrons that can break free and travel through that atomic scaffold we just saw. So the entire question of whether something conducts electricity or not, it all just boils down to one thing. How free are the electrons? So it turns out whether an electron is stuck at home or free to roam isn't just random. Oh no, it's governed by a very strict set of rules, and they come straight out of the wonderfully weird world of quantum physics. You know, unlike a ball that can roll at any speed you want, an electron inside that crystal lattice is, well, it's picky. It can only exist at very specific energy levels. You can think of them like designated parking spots for energy. An electron can be in spot A or it can be in spot B, but it can never, ever be in between.
Now, when you get billions upon billions of atoms all packed together in that lattice, those individual parking spots for energy kind of blur together. They form these wide bands of allowed energy. And trust me, understanding these bands is the key to everything.
Okay, this diagram right here, this shows you the three zones that decide it all. Down at the bottom, you have the valence band. Just think of this as home base, where electrons are normally chilling, bound to their atoms. Up top, you've got the conduction band. This is the superhighway. If an electron can get enough of an energy boost to jump up here, it's free to move around and create a current. And that space in between, that's the forbidden zone, or the band gap, an energy range where electrons just aren't allowed to be. So, the relationship between these three places, the home, the highway, and the gap, that's what determines everything. Let's see how this one simple model perfectly explains our three types of materials. First up, conductors, like our copper wire. In these materials, the valence band and the conduction band actually overlap. There is no forbidden gap at all. This means the electrons are pretty much born on the highway. It takes almost zero energy for them to start moving. And that's exactly why metals are such amazing conductors. All right, next up, an insulator, also called a dielectric, like the plastic on that wire. In this case, the forbidden zone is massive. It's a gigantic energy wall. An electron hanging out in its home band just doesn't have nearly enough energy to make that huge leap up to the conduction highway. They're just stuck. No current can flow. And now for the magic trick, semiconductors, like silicon. Here, the forbidden zone is there, but it's narrow. It's not really a wall. It's much more like a gate. If it's super cold, it acts like an insulator. But if you add just a little bit of energy, maybe from some heat or light or an electric field, some of those electrons get just enough of a kick to hop over the gate, jump into the conduction band, and start moving. So this is the perfect way to lock it in your brain. A conductor is an open highway. No tolls, no barriers. An insulator is a dead end with a giant wall. But a semiconductor, that's a road with a gate that we can actually learn to open and close whenever we want. And this ability to open and close that gate in a semiconductor, it's not just some neat physics trick. It is the literal foundation of our entire digital world. So it turns out we don't just have to rely on heat or light to control these things. We learned how to engineer them with incredible precision by intentionally adding tiny, specific impurities right into the crystal lattice. And this process has a cool name. It's called doping.
And this doping works in two main ways. If you add an impurity that has an extra electron it doesn't need, you create a surplus of free, negatively charged electrons. We call this an N-type semiconductor. But you can also add an impurity that's missing an electron. This creates a little empty spot, a hole. A nearby electron can easily hop into this hole, which leaves a new hole behind it. This moving hole acts just like a positive charge, and this creates what we call a P-type semiconductor.
Now, here's where it all comes together. When you strategically place these N-type and P-type materials right next to each other, you create something called a P-N junction. That simple little junction is the basis for the diode, which lets current flow in only one direction. And if you sandwich them together, you build the transistor, the tiny, microscopic switch that is the fundamental building block of every single computer chip ever made.
And really, that says it all. The transistor and our ability to flick it on and off super fast, representing the ones and zeros of all digital information, is what allows your phone, your laptop, and the entire internet to even exist. It all comes down to controlling that gate. So let's just recap it one last time, nice and simple. Conductors, they just let electricity flow. Dielectrics, or insulators, they just block it. But semiconductors, they give us the ultimate power. The power to control it, to switch it, to direct it, to make it do our bidding.
It's pretty wild when you stop and think about it. We have literally built our entire modern civilization by getting really, really good at telling tiny little electrons where to go and when to go there. So the real question is, what amazing things are we going to build next as we get even better at controlling the fundamental particles of our universe?